Swayam Prabha. Digital India. Educated India.
Hello all, welcome back. In the previous lecture we were discussing about different empirical equations for the measurement of infiltration. We have seen different estimation techniques such as empirical equations and also by means of theoretical equations. We have covered 3 equations related to empirical methods and theoretical methods we will see in the next class. Before that, we need to solve some of the numerical examples related to empirical equations. So, let us start solving some of the examples today. So, first let me read out the question. Observed cumulative infiltration from an infiltrometer is given in the following table. Estimate the parameters of Kostyakov equation. Infiltration data from an experiment is given to you. You need to calculate the Kostyakov parameters. We have seen Kostyakov equation in the yesterday's class. So, we need to fit the curve and find out the Kostyakov parameters. So, this is the infiltration data. Time is given in minutes and cumulative infiltration depth in centimeters. So, by making use of these data, we need to find out the parameters corresponding to Kostyakov equation. So, these are the data which are given to us, time versus cumulative infiltration depth. So, first we are going to find out the infiltration rate, and for finding out infiltration rate we need to do some calculations. So, cumulative depth is there, from that we have to find out the incremental depth. For each and every incremental time, how much is the water infiltrated into the ground, that we need to determine. So, the incremental time and incremental depth need to be calculated, that is given over here in the columns. So, this column is representing the time which is converted into hours, and after that we will calculate the incremental time, how much is the time corresponding to each increment. Now, incremental depth, you need to be very careful while solving the problem whether the cumulative infiltration depth or incremental depth is given to you, that need to be carefully understood. If the incremental depth is given to you, you can directly use that. In case the cumulative infiltration depth is given to you, we need to find out the incremental depth. So, once incremental depth is obtained, we can calculate the infiltration rate by dividing the incremental depth by the incremental time. So, we got the infiltration rate in centimeters per hour, which is listed in this column. After that, we can plot the curve corresponding to cumulative infiltration and infiltration rate. So, the green curve is representing the cumulative infiltration and infiltration rate is given by the red curve. So, infiltration rate curve, you can see it is initially it was very high, and from that it is coming down, and finally it is taking a constant value. So, this constant value is around 10.04, which we have calculated, and cumulative infiltration is always, it is infiltration depth in each and every interval is added up. Cumulative value is calculated, that is why it is an increasing curve, that is very clear from this particular graph. Now, we will move on to finding out the parameters corresponding to Kostyakov equation. Kostyakov equation corresponding to cumulative infiltration is given by f of t is equal to kk divided by 1 minus alpha t to the power 1 minus alpha. This is the expression corresponding to cumulative infiltration. In the previous slide, we have seen how the infiltration is changing. Cumulative infiltration graph and the infiltration rate graph is plotted to understand how the curve will be looking like. In the question only asked for the Kostyakov equation parameters. So, here we are going to make use of the cumulative infiltration data which is given to us. And this equation in a simplified form we are writing f of t is equal to a t to the power of b. In this a is nothing but kk divided by 1 minus alpha and b is 1 minus alpha. We need to find out kk and alpha. Kk and alpha are the Kostyakov equation parameters. So, from the given data of cumulative infiltration, we need to fit certain line, and after that we need to get the values corresponding to these parameters. So, what we are going to do, we will be taking natural log on both the sides of the equation. So, this particular equation, if you are taking natural log on both the sides, it will be taking the form ln f of t is equal to ln a plus b ln t. After that, what we are going to do, we will be taking the natural log of the cumulative infiltration data given to us and natural log of time. Time is also given to us. The data which is given to us will be converted into natural logarithms and we will plot the graph. So, these red points are showing the data points. We are plotting the graph between ln f of t and ln t. Natural logarithm of cumulative infiltration and time is calculated, and after that we are plotting those data points. So, then what we will be doing, we will be fitting a straight line corresponding to these data points. Best fitted straight line is plotted and that equation is given over here. That is y is equal to 0.699 x plus 3.315. So, this equation will be compared with this equation. So, if you look at this particular equation, this is in the form of y is equal to mx plus c. C is given by ln a and our variable is ln t over here. So, mx is given by b ln t. So, the expression corresponding to the equation corresponding to the straight line is given over here. So, we will compare this equation and this equation to get the Kostyakov equation parameters. Ln f of t is equal to 3.315 0.7 ln t, that is 0.699 is round off to 0.7. Ln f of t is equal to 3.315 0.7 ln t. So, now we can compare these two equations to get the parameters. So, these are the equations. So, here we are having ln f of t in terms of ln a and b ln t. We got the fitted line equation ln f of t is equal to 3.315 plus 0.7 ln t. So, from here itself it is clear that b is nothing but 0.7. So, b is 0.7, but actually what is b? B is 1 minus alpha. So, 1 minus alpha is equal to 0.7. So, from that we can get the parameter alpha is equal to 0.3. Now, coming to ln a is given by 3.315 from the fitted line. So, we can take the antilog and we will get the value corresponding to a as 27.52. But what is a? A is given by kk divided by 1 minus alpha. So, kk divided by 1 minus alpha is 27.52. From this we can calculate the value corresponding to kk. Kk can be calculated as 19.27. So, we have made use of the cumulative infiltration data. We have taken the natural log on t and also on cumulative infiltration data. After that we have plotted ln f of t versus ln t. Then through the points which are plotted, we have fitted a best fitted straight line, and the corresponding equation is taken and compared with the Kostyakov equation to get the Kostyakov parameters. So, that way we have found out the values corresponding to alpha and kk. So, this is our equation f of t a t to the power of b. So, here we are substituting the corresponding parameters a and b. So, you will get cumulative infiltration as 27.5 t to the power of 0.7, and infiltration rate is given by kk t to the power of minus a. So, that is taking the form 19.27 t to the power of minus 3. So, now we can make use of this particular equation, that is these two equations corresponding to cumulative infiltration and infiltration rate for calculating the cumulative infiltration and infiltration corresponding to different time. So, for this particular soil, we have calculated the Kostyakov parameters, and by making use of these equations later on we can calculate the infiltration rate and cumulative infiltration, because we have fitted the parameters by using the given data. These are the expressions corresponding to cumulative infiltration and infiltration rate. The second example is related to Horton's equation, the second equation which we have seen yesterday. So, the question is, infiltration capacity data obtained from an infiltrometer are given in the following table. Determine the parameters of the Horton's infiltration model. The infiltration data is given to you. So, you look at the data corresponding to infiltration capacity. Infiltration capacity is nothing but the infiltration rate. So, that is given over here. Even if there is any confusion whether it is infiltration capacities, units are not given, check the data. So, this is 5.6, 3.2, 2.1, that, and finally it is reaching a constant value 1. So, you can understand that infiltration value is decreasing as time increases. So, definitely this is giving you the infiltration rate. So, here units also given to you, that is in millimeters per hour, and time is given in hours, already time is in hours. So, now we need to solve this problem, that is determine the parameters of the Horton's infiltration model. Similar to that of we have done in the case of Kostyakov equation, we need to fit the curve and find out the Horton's parameter. Here you have been given the infiltration rate. In case cumulative infiltration is given to you, you need to calculate the infiltration rate as we have done in the previous problem. So, infiltration capacity I am representing by means of the notation Fp, that is Horton's equation is derived for potential infiltration, that is sufficient moisture content is available and the infiltration which we are obtaining is the potential infiltration. So, that is why I am putting the notation F of P over here, and we can calculate, this is our equation, F of P is equal to Fc plus F naught minus Fc multiplied by e to the power of minus kT. Fc is the constant rate of infiltration or the steady state of infiltration attained by the soil after certain time. So, here in this case we can observe the data, the time has reached 2 hours and around 1.5 hours it is 1.1 millimeters per hour, 1.75 hours it is 1 millimeter per hour, and at the time t is equal to 2 hours it is again 1 millimeter per hour. That means the infiltration rate has reached the steady state. So, Fc is obtained from our data. Now, F naught and F naught minus Fc multiplied by e to the power of minus kT. We need to find out the values corresponding to F naught and k. For that we will move ahead, and what we are going to do, we are going to make some adjustment with the terms Fp minus Fc is equal to F naught minus Fc e to the power of minus kT. After that again we are taking natural logarithm on both the sides. So, left hand side will be ln Fp minus Fc is equal to ln F naught minus Fc minus kT. This we have seen already in the previous lecture. So, this is in the form of y equal to mx plus c again. Y is nothing but ln Fp minus Fc and mx is representing our minus kt. So, t is our variable and m is the slope. So, if we are fitting a straight line with the data, then we can get the slope from the straight line, and that slope will be representing our parameter k, and our intercept c is given by, c will be giving you ln f naught minus fc. Once ln f naught minus fc is obtained from the graph, you can calculate the value corresponding to f naught. Let us see how the values are coming. So, here fp minus fc, we have seen it is our y. So, fp minus fc is calculated, that is our constant rate of infiltration is fc is nothing but 1. So, fp minus fc, with these values we are subtracting our steady state infiltration value, and those values are listed here in this table. Then we will find out the natural logarithm of fp minus fc and we will plot the graph. We are plotting the graph with respect to ln fp minus fc and time h. Here the x axis is the given time. The graph is plotted between ln fp minus fc and time h. So, we have marked the data points over here with the red data points. After that, what we are doing? We are fitting a best fitted straight line for these data points. So, that straight line equation is found out to be y is equal to minus 3.1 x plus 2.3466. So, that equation can be compared with this equation for finding out the Horton's parameters. So, y is equal to 3.1 x plus rounded off to 2.35. So, here you can compare minus kt and minus 3.1 x, both are representing the same value. So, you can see our variable x is nothing but t, time. So, k is equal to 3.1. So, from the graph, after fitting the straight line, directly we will get the value corresponding to exponential constant k, that is 3.1. Now, coming to the regarding the value f naught. So, for that we are having ln f naught minus fc. ln f naught minus fc is the intercept of the graph. Intercept is nothing but 2.35. So, ln f naught minus fc is 2.35. So, f naught minus fc, you can take the antilog and it will be coming out to be 10.49, and our fc is already known to us, that is 1 millimeter per hour. So, f naught is 10.49 plus 1, it will be coming to be 11.49 millimeters per hour. Now, we can substitute in this equation to get the final form of Horton's equation. So, infiltration rate corresponding to these data can be represented by this equation. Fc is 1 and f naught minus fc is 10.49 e to the power of minus 3.1 t. So, from the given data, here in this case infiltration rate only given, from the infiltration data given to us, we have calculated the Horton's parameters. The way in which we have proceeded, we are taking the natural logarithm, and after that we will get the equation in the form of a straight line, and for the data we will be fitting a straight line, and comparing these two equations we can find out the parameters related to Horton's equation. So, now where you do not have to go for doing the experiment for this particular type of soil, just for different times. So, t component is here in the exponent. So, from time 0 to certain time you can give the values and you can plot the infiltration rate, and also by integrating this curve, this equation corresponding to infiltration rate, you will get the cumulative infiltration also. So, for that particular soil, after conducting the infiltration experiments, we have fitted the Horton's equation. I hope it is clear to you how the Horton's parameters can be obtained from the given data. So, we have done two numerical examples corresponding to Kostyakov equation and also Horton's equation. Now, we know how the cumulative infiltration curve will be looking like, and also infiltration rate curve. Infiltration rate in the case of Kostyakov equation, it is given by a power relationship and in the case of Orton's equation, it is represented by means of an exponential relationship. So, once infiltration rate is there with us, we can calculate the cumulative infiltration curve by integrating the infiltration rate. So, whenever we are having the data, we can make use of those infiltration experimental data to get the parameters corresponding to empirical equations. So, these are some of the textbooks from where I have taken these problems, and so many number of exercise and example problems are there for working out and for understanding more. Here I am winding up this particular problem solving session related to empirical equations. Thank you.